Right now, the fastest thing humanity has ever built is about to hit a milestone. In November, Voyager 1 becomes the first object we've made to sit one full light day from Earth. It took 49 years. The nearest star is over 1,500 light days away, and that gap is not even close to the hardest part. Let's get right into it. Number 9, the light day problem. Voyager 1 left Earth in 1977 before most people watching this were born, and it has not slowed down since. It's coasting at about 17 kilometers per second, roughly 61,000 kilometers an hour. It still has thrusters, but all they do is nudge the antenna to keep it pointed at us. They cannot meaningfully change where it's going. No brakes, no steering, no way to change its mind. In November, it crosses 25.9 billion kilometers from Earth, which is exactly how far light travels in one day. First object we've ever built to manage it? That sounds enormous until you check the neighbors. Proxima Centauri, the closest star to our Sun, sits about 4.24 light-years away. Convert that into the same unit and it's over 1,500 light days. So after 49 years of continuous flight, Voyager has covered roughly 1/1500th of the distance to the nearest star. And it isn't even aimed at it. Here's the version that actually lands. At Voyager's speed, that trip takes about 75,000 years. Not hours. Years. Longer than farming has existed, longer than writing, cities, money, or any language currently being spoken. Voyager would still be drifting when every civilization that ever discussed it had become archaeology. And the ugly part is that Voyager isn't slow because we were being cheap. It's riding the fastest push we could physically give it. Gravity assists, essentially stealing a little orbital momentum from Jupiter and Saturn on the way past. That was the cheat code. The cheat code bought us one light day in half a century. So the obvious response is the one everybody has. Fine, build something faster, strap on more fuel, go. That instinct is completely reasonable. It's also exactly where the physics stops being polite. Number 8, the fuel math fails. Rockets have one deeply annoying property. They have to carry their fuel, which means the fuel has to be accelerated too, which means you need more fuel to move the fuel. Konstantin Tsiolkovsky worked out the consequence back in 1903, and it's still the meanest equation in aerospace. Speed doesn't grow with fuel. It grows with the logarithm of fuel. You don't add to the tank, you multiply it. Put real numbers in, and it gets funny in a bleak way. The best chemical rockets we have throw exhaust out the back at roughly 4.5 kilometers per second. Suppose you're not even greedy. You just want 1% of light speed, about 3,000 kilometers per second. Run the equation, and the ship has to start out on the order of 10 to the 280th power times heavier than the piece that actually arrives. For scale, the entire observable universe contains something like 10 to the 80th atoms. Total, you'd need vastly more mass than exists, all of it converted into rocket fuel, to push one small capsule to 1% of light, and 1% of light still means over 4 centuries to reach Proxima. This is the part people consistently underestimate. Chemical rockets aren't disqualified from interstellar travel because they're underfunded or old-fashioned or waiting on a smarter engineer. They're disqualified by arithmetic. There is no clever nozzle, no exotic fuel blend, no billionaire with a big enough checkbook, which is why serious proposals stopped asking chemistry for help decades ago and went straight to the only thing with enough energy packed into a kilogram: nuclear reactions. And someone did design that ship. Fully. With a mass budget, a fuel supply chain, and a construction schedule. It has a flaw you'll spot in about 4 seconds. Number 7, the starship that can't stop. Between 1973 and 1978, the British Interplanetary Society ran a study called Project Daedalus, led by the engineer Alan Bond. This was not a napkin sketch. 13 volunteers produced over 200 pages of real engineering, mass budgets, trade-off studies, structural analysis, trying to prove a starship could be built using physics we already understood. The design is genuinely beautiful and completely unhinged. Daedalus was a 2-stage fusion rocket assembled in Earth orbit, weighing 54,000 tons. Of that, 50,000 tons was fuel and 500 tons was the actual science payload. Its engine would detonate pellets of deuterium and helium. 250 times every second, with a magnetic nozzle aiming the plasma out the back. It would burn for nearly 4 years, coast at 12% of light speed, and reach Barnard's star in about 50. Small problem with the fuel. Helium-3 barely exists on Earth. The study solution was to mine roughly 30,000 tons of it out of the atmosphere of Jupiter using robotic factories held aloft by hot air balloon suits across a 20-year industrial program. That's not the punchline. That's a supporting detail. Here's the punchline. Daedalus has no brakes, it cannot decelerate. It was designed as a flyby from the start because stopping costs roughly as much energy as leaving did. You'd need a second engine and a second mountain of fuel purely to cancel the speed you spent decades building. So the crowning achievement of the most rigorous starship design ever produced is this. After 20 years of strip mining Jupiter and 50 years of flight, it crosses the entire target system in about 2 days, takes photographs, and continues into the dark forever. To actually stop somewhere, you need fuel carrying far more energy per kilogram. There's exactly one candidate. Number 6, fuel worth more than civilization. Antimatter isn't the best fuel we currently have. It's the best fuel physics permits, and nothing will ever beat it. Nuclear fission converts roughly 0.1% of its mass into energy. Fusion does somewhat better. Antimatter, annihilating with ordinary matter, converts essentially all of it, every gram, completely, into pure energy. A gram of it meeting a gram of normal matter releases something in the range of tens of kilotons of TNT. That's several Hiroshimas out of a speck you'd need a microscope to see. So obviously we build the tank. Here's where that stands. CERN operates a facility genuinely called the Antimatter Factory. By CERN's own published numbers, if that factory ran non-stop for an entire year, every antiproton it produced would add up to roughly 500 joules of energy. 500 joules will light a 100-watt bulb for 5 seconds. Not power a city, not launch a probe. 5 seconds. And the anti-hydrogen they can actually trap is smaller still. A full year of it, annihilating at once, would release a few thousandths of a joule, which is about what you spend tapping your phone screen. Estimates for how long it would take to accumulate a single gram range from hundreds of millions of years to numbers that outrun the age of the universe, depending on whose assumptions you use. They disagree wildly. None of them disagree about the part that matters, which is that a starship would want it by the ton. And you can't just keep it in a tank. Antimatter annihilates the instant it touches anything, including its own container, so it has to hang suspended in a vacuum inside magnetic fields, never contacting a surface for the entire voyage. Lose power for a moment and your fuel supply becomes the disaster. Fine, new plan, and it's a genuinely brilliant one. If carrying fuel is the problem, don't carry any. Leave the engine at home and push the ship from Earth. That plan is real, it's funded, and it breaks for a reason almost nobody predicts. Number 5, space is not empty. In 2016, Breakthrough Starshot put $100 million behind an idea that dodges the rocket equation completely. Instead of a giant ship hauling fuel, you build gram-scale probes, chips attached to a thin reflective sail, and shove them with an enormous laser array on the ground. The engine stays on Earth. The spacecraft is roughly a postage stamp. Target speed is 20% of light, which puts Alpha Centauri about 20 years away. It's elegant. It's the most credible interstellar concept anyone has produced. And then a team of astrophysicists, Huang, Lazarian, Burkhardt, and Loeb, sat down in 2017 and calculated what the journey does to the probe. Interstellar space holds roughly 1 atom per cubic centimeter. That's emptier than any vacuum we can manufacture on Earth. Functionally nothing. But at 20% of light speed, functionally nothing starts behaving like a sandblaster. Their work found that gas bombardment alone could eat about 1/10 of a millimeter into a quartz surface over the trip to Alpha Centauri. That's the mild version. Dust is worse. A single interstellar dust grain 1/10 of a micron across contains something like 1 billion iron atoms, and each of those atoms punches a damage track a few nanometers wide. Hit one, and the impact site explosively evaporates, blowing a crater into your spacecraft. Their suggested fix was a millimeter of graphite mounted on the front like a shield, which is fine for a chip. Now, scale it to a crewed vessel with thousands of square meters of frontal area, sweeping up thousands of times more of everything, for centuries. That leaves one option: slow down. Take the long trip, send people instead of postage stamps. Space has opinions about people. Number 4, your body isn't rated for this. Here's what deep space does to a body once you leave the magnetic field that's been quietly protecting you your entire life. Galactic cosmic rays are not the polite radiation of a dental X-ray. They're atomic nuclei, stripped bare, and accelerated to near light speed. Protons and heavier things like iron nuclei that tear through tissue in a line rather than a scatter. NASA links extended exposure to raise cancer risk, cardiovascular disease, central nervous system effects, cataracts, and wounds that heal badly. NASA's current career limit sits below 600 millisieverts for an astronaut's entire flying life. An interstellar voyage is counted in centuries. So you add shielding, and the universe does something that feels almost personal. When those heavy nuclei hit a shield, they don't simply stop. They shatter into showers of secondary particles, neutrons included, which are themselves very good at wrecking tissue. Shielding doesn't delete the radiation field, it rearranges it, and the relationship between thickness, material, mass, and crew dose is nothing like thicker wall equals proportionally safer. The real fix is a lot of mass. Meters of it, water, rock, anything dense, which is inconvenient because mass is exactly what the rocket equation punishes exponentially. The shield and the engine want opposite things, and they want them for the entire trip. Meanwhile, in zero gravity, your skeleton quietly resigns. NASA reports weight-bearing bones losing roughly 1 to 1.5% of their density every month on 4 to 6 month missions without effective countermeasures. Muscle weakens too. Fluid shifts upward into the skull. And vision changes in ways researchers are still working out. Solve that with a spinning ship for artificial gravity, and you've just added structure, moving parts, and fresh ways to fail. So stop pretending anyone survives this personally. Accept the centuries. Send a crew that has children who have children. Now you need to know how many. Number 3, the minimum human population. Ask how many people you'd need on a multi-generational ship, and the honest answer is that it's not a crew question. It's a population genetics question, and the numbers are unsettling. In 2018, astrophysicist Frédéric Morin and physicist Camille Bellufi published work using a Monte Carlo simulation called Heritage, software that runs a whole voyage thousands of times over, modeling births, deaths, accidents, infertility, and inbreeding across generations. They ran it for a 6,300-year trip to Proxima b at speeds achievable with current technology. Here's how the numbers moved. Success rates climbed as the starting population grew, then leveled off. Somewhere around 94 to 98%, once the crew reached 68 people. 98 settlers was the smallest starting population that came through their tested runs fully successful. Go meaningfully below that, and the population breeds itself into a genetic dead end long before anybody sees another star. But that's one model with one set of assumptions. In 2023, Satoshi Sano ran the problem again while letting the reproductive parameters fluctuate the way they actually would over a real voyage, infertility, initial genetic diversity, children per woman, and got a critical crew size somewhere between 1,400 and 6,800. World ship studies have modeled departures of 14,000. Researchers genuinely disagree here, and that disagreement is the point. Nobody knows the real figure, and being wrong is unrecoverable. Notice what quietly happened to the mission, though. Those papers only work under what they call adaptive social engineering, rules revised continuously, governing who may have children, at what age, with whom, and how many. You're no longer commanding a spacecraft, you're administering a closed society with mandatory reproduction policy for 200 generations. And that society has to eat, drink, and breathe inside a sealed box for 6,000 years. We tried that. In Arizona, it took 16 months to start going wrong. Number 2, the tiny Earth that suffocated. On the 26th of September 1991, 8 people were sealed inside the Biosphere 2, a 3-acre glass and steel structure near Oracle, Arizona, containing a rainforest, a savanna, a small ocean, farmland, and its own atmosphere. It was the most serious attempt ever made to build a miniature Earth. 2 years. Closed. The oxygen started disappearing almost immediately. It began at the normal 20.9% and fell steadily. 16 months in, it had dropped to roughly 14%, the equivalent of trying to live at around 13,000 feet of altitude. The crew reported exhaustion, trouble sleeping, and difficulty thinking clearly. Eventually, the seal that defined the entire experiment had to be broken so oxygen could be brought in from outside. The mystery was where it went. If microbes were consuming oxygen, carbon dioxide should have risen to match. It didn't. The bookkeeping wouldn't balance, and for months nobody could explain it. The answer, published in 1994, was the building. The soils had been loaded with organic matter to make crops grow, so microbes respired far faster than the young plants could photosynthesize. And the carbon dioxide those microbes produced was reacting with the enormous amount of exposed concrete throughout the structure, binding into calcium carbonate, around 26 tons of it locked into the walls. The oxygen went into the soil. The evidence went into the concrete. Sit with that. Highly capable people, a full biosphere, sunlight, and an entire planet's worth of engineering support one phone call away. 16 months, defeated by dirt and their own foundations. Nobody modeled the walls as part of the ecosystem because on Earth the walls never are. Which brings us to the thing that actually stops us, and it isn't distance. Number one, the machine that must never break. Everything so far has been a fuel problem, a biology problem, a numbers problem, solvable in principle. The real barrier is stranger, and it's the one nobody puts on a poster. A starship has to keep working, not for a warranty period, for centuries with no factory, no spare parts, no supply chain, and no Earth. The world ship literature has actually tried to size this. A 2020 feasibility review concluded that a vessel like that would require a maintenance system capable of detecting, replacing, and repairing several components per second continuously for the entire voyage. Not a repair crew. You don't pack enough spares for 6,000 years, you pack the ability to manufacture spares, which means machines that make parts, tools that repair those machines, raw material to feed them, and the preserved knowledge to run the whole chain for 200 generations. Compare that to what we've actually built. The International Space Station stays alive because cargo ships resupply it constantly and engineers on the ground diagnose it around the clock. And Voyager, our great success story, is dying gracefully. Its nuclear generator loses about 4 watts of usable power every single year, so NASA keeps switching off heaters and instruments one at a time to buy more mission. Another one went dark this April. Sometime in the 2030s, the signal fades below what our antennas can hear, not destroyed, just gone quiet in a way nobody can fix. So the honest sentence is this: nothing we've covered violates a law of physics. Antimatter is real. Fusion is real. Closed ecosystems are real. There's no cosmic sign reading no exit. But every single barrier, energy, radiation, genetics, maintenance, time, is one where the required scale sits absurdly far beyond anything humans have ever done, and several of them fight each other directly. More shielding means more mass. More people means a bigger habitat. A bigger habitat means more propulsion and more maintenance. A longer trip means more generations and more chances for one small error to become permanent. Leaving isn't forbidden, it's just that the ship isn't a vehicle at all. It's a world. And we have never successfully built one of those. That's all for today. I'll be making similar videos in the future. Subscribe to see them.